In Lesson 6.1, we're going to learn what a system of linear equations is. And we're going to start by this application problem. It says two runners run a 40-yard dash at speeds shown in the diagram. Runner 1 starts 4 seconds before runner 2 to make the race more competitive. Will runner 2 pass runner 1 and tell me how you know? So the first thing that we need to do is look at the pace that they run. So runner 2 runs 8 yards per second, and runner 1 runs 4 yards per second. The other thing you have to look at is that they are running a 40-yard dash. So what you could do is you could figure out how long it takes runner 2 to run 40 yards if he runs 8 yards per second. So you would take 40 and divide it by 8, and that gives you 5 seconds. So runner 2, let's undo that. So again, we're going to take the 40 yards and divide it by 8 yards per second. So it'll take him 5 seconds to run. If we take a look at runner 1, he runs 4 yards per second. So we're going to take 40 and divide it by 4 yards per second. So that'll take him 10 seconds. And the question is, will runner 2 pass runner 1 if runner 1 gets a 4-second head start? So after that 4-second head start, it'll still take him 6 seconds to finish, but runner 2 will finish in 5 seconds. So yes, runner 2 will pass runner 1. Now we're going to consider a 3-second head start instead of a 4-second head start. So let's take a look at a table. So runner 1 is still running 4 yards per second, and at time 0, runner 1 has gone 0 yards, so we're just going to fill that in. After 1 second, he has gone 4 yards. After 2 seconds, he's gone 8. 3 is 12, and 4 is 16 yards. Runner 2, remember, he has to wait, so at time equals 0, he hasn't started yet. At time equals 1, he hasn't started yet. At time is 2, he hasn't started yet. So these are all zeros, and at 3 seconds, he hasn't started yet. So at 3 is when he starts, so at 4 seconds, he has gone 8 yards. And then from there, it will go up 8 every time. So now, let's take a look at the graphs of those. So I'm going to put runner 1 in red, like I have all of his numbers. I already have my axes labeled, and I'm going to title this 40-yard dash. So my title is 40-yard dash. Okay, so in red, I have the points 0, 0, and then I have the point 1, 4, so I'm going to come up with my scale. So I have put my scale on that graph. So 0, 0 is a point on the graph. 1, 4 is a point on the graph. So I went ahead and plotted all the points that runner 1 would have in a table up to 40 yards. Now with runner 2, he has to wait until 3 seconds have passed before he can start. So he is right here at 3 seconds. He is still on the start line. and then at 4 seconds he will have gone 8 yards. And now you can see all of the blue points are runner 2. So I went up 8 yards for every circle. So I can see that these are the points for runner 2 in blue. These are the points for runner 1 in red. Now I've connected the dots, and you can see that the two runners will cross paths right there. And that is the solution to when runner 2 will reach runner 1. And here you can see I have filled in the equations. Now the red one should be pretty easy to understand. The y-intercept is 0, and it goes up 4 yards for every second, up 4 over 1, because he traveled 4 yards per second. So that's the equation for runner 1. Now for runner 2, it's a little bit more difficult because we don't know the y-intercept. But remember, he had to wait 3 seconds before he started. So what you need to do is figure out how far he would have run in 3 seconds. Remember, his pace was 8 yards per second. So he would have been 24 yards behind the start line if he started running when the shotgun ran off, when the race started. So that means that negative 24 that you see there is where he would be on the y-axis at the start of the race if he started at the same time but behind the start line. Alright, let's move on to the next page of our notes. You should pause the video and copy down those vocabulary terms. And when you're done with that, go ahead and resume playing. Now I'm going to talk about the definition of a system of linear equations, which is two or more equations that form lines when they are graphed. So over here in this orange box, we have examples of systems of linear equations. We have two equations here, and both of those will form a line. Notice they're in y equals mx plus b form, and we should know that that forms a line now. Here are two equations. They also have y equals mx plus b form, so those are both lines as well. Now these we have talked about already. If you just have x equals a number, then that means it's a vertical line, which goes up and down. If we just have y equals a number, it's a horizontal line. So this is also a system of linear equations. If you look at the purple box, none of those are systems because, first of all, it requires at least two, and you only have one in each example there. Another is that you have to have equations. So if you look at this, that's not even an equation, so that can't be a system of equations. And that's the same thing here. So those are non-examples. What you need to understand is that a solution is a point that makes all of the equations in the system true. So when you're asked down at the bottom, is 2 for a solution, that means when you plug in x and y, the 2 and the 4, it'll work in both equations. We'll get to that in just a moment. Let's take a look at this got it. In this example here, that is not a system of linear equations because, remember, we have to have 2. Here we only have 1, so I'm going to put no for that one. For the second example, we have x equals 5. That's a vertical line, and y equals x plus 1. That is y equals mx plus b form. So this would be a system of linear equations. So I'm going to put yes for that one. And then the third one, we have y equals 2x, so that's y equals mx plus b, where the b is 0. And we have y equals 3.2x minus 8, that is also y equals mx plus b form. So example 3 is a yes. So now we're ready to see if 2, 4 is a solution to part A. So again, we're going to take 2, 4, and I'm going to do my work over here. You have enough room on your paper to do it. So the point 2, 4 gives you an x and a y. So you're going to take y equals 2x, and you're going to see if that works. So I'm going to take x equals 2, and I'm going to put that in for my x. And I also see that y equals 4, so I'm going to put that in for my y. So I end up with 4 equals 2 times my x value, which was 2. And I want to know, does that work? Does 4 equal 2 times 2? 4 equals 4, so yes, it works. Now keep in mind, up here it says it has to make all of the equations true. So it made the first one here true. Does it make the second one true? So now we have to test that. So you can see that I'm going to plug in 2 for this x, and I'm going to plug in 4 for the y. So we have 4 equals 6 times the x value, which is 2, minus 8. So I want to know, does that work? So is 4 equal to 12 minus 8? Yes, it is. 4 equals 4. So that means that this is a solution. So now it's time to see if part B works. So I'm going to take 2 and put it in for the x. I'm going to take 4 and put it in for the y. So here I will have 2 minus 4 equals negative 1. So I'm going to ask, does that make sense? Does that work? 2 minus 4 is negative 2. Does negative 2 equal negative 1? No. So that means that it is not a solution. So make sure that you check it in both, unless it doesn't work in the first one. So if it works in the first one, you have to check the second one. Let's move to the third page. With the third page, you're going to plug 3 in for x and negative 4 in for y to see if they both work. So please do that. So this is what you should set up, and then you're asking, does it work? Then I figured out that 3 times 3 was 9. 9 plus negative 4 is 5, so I put a check mark. And then over on the other equation, we have minus and negative, so we're going to add opposite. So it becomes 3 plus 4, which is 7, so that works. So the answer to this got it is yes. All right. And then the final two are asking us to write a system of equations for each scenario. So here I can see that alligator 1 starts at 4 pounds and increases 1.5 pounds per month. So you should see that the per month is a huge indicator that that's the slope. The initial weight is our starting point, so that's our y-intercept. So the equation for alligator 1 is y equals the rate or slope, which is 1.5, x, plus the initial amount, or the y-intercept, which is positive 4. So that's for alligator 1. For alligator 2, we have y equals our rate or slope, which in this case is 1 pound per month, so 1x, or just x, plus our initial weight, which is 6. So right here I have a system of equations because I have 2 or more equations that represent what's in the table. And finally down here I can see that the rate is this bottom and the initial amount is the top. So we have an equation for Greenland sharks, and we have a different equation for the spiny dogfish shark. So for Greenland sharks, we will have y equals the rate or slope, which is 0.75 centimeters per year, so times x, plus our initial value, which is 37. So that's for the Greenland shark. And now we have an equation for the spiny dogfish shark, which is y equals the rate, 1.5 centimeters per year, so the rate times x, or the slope times x, plus the y-intercept, or the initial value, which is 22. So here we have an equation, or a system of equations, because it's 2 or more equations that represent the information in the table. And that is it for your notes.